much bigger than the gravitational force. So just gravity doesn't really play a role in this stage over here. So when you can write down the force acting on the electron, write F equals ma. There's also some conditions that you impose on the orbital angular momentum of the electron, and you end up. I'm going to do the derivation later on when we get, I think it's in chapter 37, but you end up with the energy of the electron being equal to minus 13.6. It's actually some number in joules, but then you have like 10 to the minus 18 or something joules. It's a very small number, so introduce a new unit, which is called the electron volt, and it's minus 13.6 electron volts. And then you have an n squared that appears in the denominator, and then you say, okay, so I'm going to call this the energy when n has that value. And in this case, n can be 1, 2, 3, 4, blah, blah, blah. Just like over here. There is a restriction on the values of n, which I didn't highlight, but n cannot just be any value. So when you solve this problem, n, again, cannot just be any value. And in atomic physics, n is called the principal quantum number, because as it turns out, there are other quantum numbers involved. There's one associated with the spin of the electron. Well, anyway, quantum number, instead of just being called n. Oops. Write with a pointer. So you have this. It's restricted to values 1. 0 doesn't. I mean, what would you have if you had 0? Then this would be infinity, minus infinity, right? So 0 is not allowed. So instead of talking about frequency, you talk about energy in this case. But you have this n showing up, where n is just some number that can take on any one of these positive integers, 1, 2, 3, 4, and so on, up to infinity. Same thing over here, right? So n can be 1, 2, 3, 4, just a positive integer. And if I did the same thing as I did over there, let's say I said that n equals 1, then E, in fact, normally what you do is, you say, I'm going to draw an energy level diagram. So let's say this is energy, E, right? And you say, okay, I'm going to call this n equals 1. So if that's n equals 1, what will be, right? If n is equal to 1, then E1 will be minus 13.6 divided by 1 squared, which is just minus 13.6. And so you write this energy like this. E1 equals minus 13.6 electron volts. And then, what if we have n equals 2? So then you write E2 equals minus 13.6 divided by 2 squared. And somehow, minus 3.4 rings a bell. You might want to check me on that. So then, actually, minus 3.4 is a bigger number than minus 13.6. It is more to the right in the number line. So it's a higher energy. So n equals 2. Right? The energy of that is minus, is it 3.4? Those of you with a calculator, just double check and correct me if I'm wrong. And if n is equal to 3, then E3 will be minus 13.6 electron volts divided by 3 squared, divided by 9. And somehow minus 1.51 rings a bell in my brain. So double check me again, please, and correct me if I'm wrong. So this is E3, it's minus, it somehow looks good, but I could be wrong. And then if n equals 4, E4 would be minus 13.6 electron volts divided by 16, and minus 0.85, is it? I think. 84. 84. Minus 8.84? Okay, thank you.
It's 8.8375.
Okay, thank you. So then, this is 4. So this is minus point. I'll stop with this one. All right, and then you can keep going like this, right? And then, you have n equals infinity, and that's when the energy of the electron is 0.
You were right. I put a number wrong.
So it's minus 8.25.
0.85.
Yeah. Thank you for checking. So, when just in this, just making a connection between that discussion and this one over here, n equals 1, right, is when the energy of the electron is the lowest. Like in this case, that's when the frequency was the lowest. So this is called the fundamental frequency. And remember that I said it could have been called the ground frequency? Well, this one is not called the fundamental energy. This is called the ground state energy. Which, you're familiar with, right? So it's called the ground state. The state is the situation that the thing is in, so it's the state so that the energy is the lowest, like if the thing is on the ground. Now, n equals 2, there are two names that you can give to n equals 2. n equals 2, you can call it the ground state is like the first allowed state. And, or maybe I'll call this the first allowed state. Now, n equals 2 is the second allowed state. Sort of like the second harmonic. But another name given to this is, well, the ground state is when the system is at. If you just leave it alone, you give it time, it'll find this lowest energy state. And so n equals 2 corresponds to the first state above the ground state. So it's called the first excited state. Like the first overtone over there. But it's not called the first overtone state, it's called the first excited state. The n equals 3 is the second excited state. Or, the third allowed state. Usually people call it the second excited state, the first excited state, the ground state. Usually here, this is the fundamental frequency. And here people can either use, the second harmonic. I guess in physics people like to use that, but people in music and so on, they like to call it the first overtone. But or they're both widely used over here. In this case, the first excited state, second excited state, the ground state is what's more widely used. The interesting thing, the connection that I want to make, another connection that I want to make with this is the following. If that electron is bound to go around the proton, then its energy is negative. Having a negative energy means that the electron is bound to orbit around the proton. And when the electron energy becomes equal to 0, when you add the kinetic energy to the electrical potential energy, when it is equal to 0, that's when the electron breaks free of the proton. And if the energy of the electron is more than 0, so that it's positive, then over here, this would be positive energy levels. Then what happens over here is that all of these levels are allowed. It's not, you don't have, like, if the energy is negative, the electron is bound to go around the proton, and the energy just can't be any value. It's got to be this, or that, or that, or that. And because the energy can only be one of these values, then the energy is quantized. And that's because we've put, if it's quantized, it can only be this or that or that or that. Because we put a restriction on where the electron can be. Well, it's gotta be around the proton, right? It's like it's been restricted to orbit around the proton, so it's like you have restricted the space to it. In the case of the string, notice that we gave the string a particular length. So there was a particular length, and that restriction imposes this, like quantized values for, frequencies, the normal mode of vibrations, right? So it's either fundamental frequency, the second harmonic, the third harmonic, and so on. So the fact that we fixed the length of the thing, we restricted the length of the string to a particular value, that imposed some, that brought about quantization. In that case, you talk about the quantization in the frequency, whereas in the case of the electron, normally you are concerned with the quantization in the energy. And so, just, this here, the energy can be any value, if it's positive. And this is called a continuum, because it is not quantized. And that's when the electron is free. In fact, normally they like to ask you this question. Suppose there is an electron in the ground state. And then they ask you, what is the quantization energy of that state? Well, the ionization energy of that state. The ionization energy is the minimum energy that would have to be supplied to the electron so that the electron breaks free of the proton. So that the hydrogen atom is ionized, ionization energy. Well, it's the minimum energy. So the minimum energy will be the energy that will take it so that its energy is going to be 0. Well, if the energy of the electron is minus 13.6 electron volts and you want its energy to be 0 so that it breaks